Okay, welcome everybody. My name is Kevin Fleming. Many of you have met me before, many of you haven't. I work for Digium as the Director of Software Technologies, which is a big title. It basically means I get to help design software that we build. So what we're going to talk about here today is asterisk SCF development. This is the first time we've talked about this. I guess we should start with some background first of all. How many of you know what asterisk SCF is already? Half the room, that's good. Hopefully some of you were at AstroCon last year and got to see the big flashy demonstration that we did. That was a lot of fun. I'm glad we're not doing that again this year. That was a lot of work. So, okay, so another couple questions. Since this is very development oriented, is this a bit loud? I don't know your name, I'm sorry. Is this a bit loud? It sounds a little loud to me. Maybe I'm just hearing more than I'm expecting. Okay. So unlike asterisk SCF is built in C++ and using a lot of object-oriented technologies, which means doing development of asterisk SCF components and add-ons and things has to be done in object-oriented programming languages. In other words, not C, not Bash, lots of other things like that. So how many of you have experience developing even relatively small applications in true object-oriented programming languages, things like C++, Python, Ruby? Okay, cool, lots. What's that? Sure, C#, all those things. Even Visual Basic.NET would even be fine, yes, absolutely. Probably not Fortran.NET, but the rest of them would be fine, yes. Right, okay, well that's good because I don't want to talk about some of these things and have you not understand what we're talking about when we say things like inheritance and classes and types and things, because those are very relevant here. So, all right, I think we'll get going. So this is essentially what we're going to do in this session today. It's going to be roughly 3 hours, just like the morning session was. There is a break sometime this afternoon. I'm not sure exactly what time it is, but probably 3 o'clock. Okay, so it'll be towards the latter part of the time then, so that's good. So we're going to talk about what asterisk SCF is a bit. I'm not going to go into an enormous amount of detail. Obviously, a lot of that was done last year at AstroCon and is on our wiki that you can go read about. Josh Kolp and Ken Hunt will also be spending time talking to you today about some of these topics. We'll be kind of handing things back and forth as we go through various parts of this today. So we'll go through some basics of how you actually get access to the asterisk SCF code and build it, put it on your machine, what APIs in asterisk SCF look like, how a developer would actually interact with asterisk SCF, the components that we've built so far. Obviously, since this is a brand new product, which we haven't even, or new project, which we haven't even had the first release of yet, it's fairly minimal, especially for those of you used to using asterisk. The feature list of asterisk SCF is pretty short compared to that in asterisk, but it's a very good starting point right now. Then we'll talk some more about how those components have actually been built. There will be a walkthrough with, I guess it's a sequence diagram or flowcharts or something that actually shows how the components interact for the basic thing of a SIP call going through the system from one SIP endpoint to another, how all the components interact. Then I'll be getting back up here and talking about how testing fits into the asterisk SCF world and how there's community involvement, of course, which is people like you. Were you trying to get my attention, Brian? Okay. All right. So this is really basic. Like I said, we're not going to spend a lot of time talking about this, but there are some really, really significant fundamental differences between asterisk SCF and asterisk. For that matter, there are big differences between asterisk SCF and most communications software applications that exist, period. The biggest one being it's a lot of small components that talk to each other over a messaging system, which we'll be talking about here in a bit. That messaging system, of course, can be used for them to talk to each other on the same machine, across machines on a network, across machines, multiple networks in multiple locations, whatever makes sense for the way you've deployed it. It also means you can have as many copies of those components as you like. There's ways to do redundancy with live call failover, which is what we demonstrated last year. There's ways to plug in additional components to modify the behavior of the system without actually having to modify the source code of the components at all, and lots of other things that this model brings. In addition to things like, of course, scalability, being able to have 100 of the component instead of just 2, if that's what your load requires, and redundancy and all kinds of things along those lines. So this is a really simple, well, I guess a relatively simple diagram that just shows that each of these machines, which presumably would be servers in your network, are providing instances of different pieces of the overall puzzle that ends up being a working system, as opposed to every one of them having a copy of the whole system on it and only using part of it. Each of these is just doing a specific function. So this is a quote, which I think Ken found from somewhere, that's actually very relevant. And you've probably all experienced this because, you know, everything is in the cloud now. I have to throw that in because Josh doesn't like that. So everybody knows, right, that, you know, you use Gmail, you use Amazon, you use whatever, and those systems fail, and you're reliant upon those things to work. Well, the same thing is true here. If you have a deployed asterisk on a single machine, it's fairly easy to wrap your head around making sure that machine is stable and everything works and continues to work and all that kind of stuff. When you have deployed something more complicated like asterisk SCF and it ends up being on 25 machines and you've got to make sure that they're all working correctly and all communicating with each other properly, there's a lot of opportunity for things to go wrong. Of course, there's also a lot of opportunity for the system to work really, really well. With that power comes responsibility. I guess that's another quote that comes from somewhere. So this is one of those cases where if you're using a system like this, especially one that you haven't deployed yourself, gaining an understanding of how all of the pieces work and how they interact is going to be very, very important for you. Now, I've kind of highlighted some of the reasons why we went this direction in the first place. This was really, these ideas here, these goals, were the reasons that we started building asterisk SCF at all in the first place. There are parts of the way that asterisk works that to achieve some fairly fundamental things like live call failover, for example, it would require so much ripping apart and rebuilding of asterisk that the result wouldn't be asterisk anymore. So rather than do that, we went in this direction. And so these are the driving forces behind how we are building what we're building. We want to make something that people can use to do things that they couldn't do with asterisk and even other similar applications before. So there are some fairly obvious concerns that people will have when you look at a system like this. Even if you deployed all of the asterisk SCF components on a single machine, and that machine was the same specification, CPU, RAM, hard drives, everything else, as a machine that you put asterisk 10 on, it is highly likely that you will not be able to achieve the same raw call throughput performance on that machine running asterisk SCF as you would running asterisk 10. That is the nature of the fact that everything is broken up into individual components and they all have to talk to each other. That adds latency, as the first bullet point talks to here. Now, depending on your application, that may not actually end up being a problem at all. Obviously, hardware keeps getting a whole lot faster. And another area where this becomes less of a concern is hardware, the word we've been using, is getting wider. So nobody buys servers with 10 gigahertz CPUs in them. They don't make them. But they go buy machines with 24 CPUs or 32 CPUs or something like that. Well, in traditional applications like asterisk and lots of others, it's very difficult to take advantage of that horizontal scaling because the software is not broken up into individual components that talk to each other. Asterisk SCF can take care of all that stuff. And then this other point is a little harder to describe, but I kind of touched on it before. It is going to be harder to manage. It's harder to understand how all of these pieces fit together than it is in a single application. Especially from the developer's point of view, you might start looking at some of this stuff and feel really overwhelmed. How would I ever make this work? Do I have to worry about where these components live and which one is currently active if the system just failed over from system A to system B, and all kinds of other things like that. So we've chosen a platform to build this on top of, a messaging platform to build this on top of that insulates you from a lot of that. And then a lot of the work we've done just adds more layers of insulation on top of that to make it even easier for you to work with the system as a developer. So that platform is called ICE. Stands for Internet Communications Engine. It comes from a company in Florida called Zero C. I'm going to go through some details about it here in just a minute. But these are really, this is the 15-second overview of what ICE is. It is a toolkit that is used to allow you to build object-oriented distributed applications, things where the components are running in separate processes maybe on different machines, maybe distributed across a wide area network, and still have very straightforward means of communication amongst them. There's a lot of reasons we chose it. This is the majority of the big reasons why we did. Obviously, platform support is very important. People are used to being able to run asterisk on lots of different operating systems and lots of different hardware. It also was important to us that it not restrict you in what programming languages you could go build components in. We've chosen to write all of our components, except for one, in C++, because that was just our choice. It's what we're more comfortable moving to. But there's no reason you should have to do that if you don't want to. And a prime example is, the gentleman mentioned over here, .NET. There are lots of people out there deploying communications platforms to build applications inside companies where the bulk of the data that the system is going to use to make its decisions lives in Microsoft land, I guess would be the way to put it. It lives in Microsoft database servers and Active Directory and Exchange and all kinds of other things. And they have application developers who use those all day long. If you go to those application developers and say, yes, we've just put in this wonderful new communications platform and you're going to be able to control the call center aspects of it and give us data about the customers and link things together, but you're going to have to write it all in Python and run it on a Linux machine, they're going to say, no, we're not doing that. We're not even going down that road. Well, that's not an issue here because ICE, and that's all the APIs we've built and everything else, are natively supported in all those languages that you see up there. And there's probably even some others. And ActionScript just got released like 2 weeks ago. ActionScript is what is inside Flash, so now it's actually possible to build asterisk SCF plugin components that run in Flash in a browser, for example. In addition to it being a messaging platform that just lets things talk to each other, ICE also has a lot of other useful features, some of which we already use in asterisk SCF, things like event and message distribution, being able to do firewall traversal so that you can run applications on a handheld device on the public internet and connect to services on a private network inside of a firewall, and lots of other things like that. And then obviously, since asterisk is open source and asterisk SCF is open source, we needed something that would be compatible licensing-wise, and ICE definitely fills that bill. So let me switch presentations here real quick. This is actually a presentation from the people who make ICE. So that's not me. That's a different person. And we're not going to go through all of this. It's quite long. But I will go through some of the highlights of it so you can get an idea of what ICE is all about. So as we said, the reason we chose this and what ICE was designed for was being able to build applications that could scale massively and not have to deal with that massive scaling in the code that you write yourself. In addition, fault tolerance has become very, very important. Obviously, many of you probably use asterisk now in environments that were not envisioned in 1999 when the first version of asterisk was pushed out onto the internet, where people are now using it for tens, hundreds of thousands, millions of calls a day, a week, in applications where downtime is incredibly expensive, and even now in applications where the loss of calls are expensive. And even if you get on beyond, the traditional like life safety things like 911 or whatever you want to consider, where those kind of calls are of course very important and you don't want them to get dropped, there are even normal business applications, people calling into call centers for companies to buy products, where if their call gets dropped, they might not call back. And if their call gets dropped, that company might have just lost a $500 sale. So those are important things that are becoming much more important as communications has moved from being on big pieces of proprietary hardware that you stuck off in a closet that were designed to run for 50 years as long as nobody ever touched them and you never had to worry about that. It's all moved to software running on commodity hardware now on IP networks. Well, along with that, the flexibility that we've gained, we've also gained some risk, I guess would be the nice way to put that. The hardware is not designed the way that traditional telephony hardware was. So that means software has to be designed to provide you that. It has to be designed in a way that you can achieve those levels of reliability without having to sacrifice what you wanted to do before. So And I've already talked about what the last bullet point is there, so we won't go about that. So again, this is some very basic stuff about ICE, you know, the typical marketing bullet points kinds of things. Many of these, they're really there to make it easier for the user, the developer, to build things using ICE. They aren't necessary for the tool to work. They're just there to make it easier for you to use. And a lot of what's going to be talked about this afternoon, you'll see examples of what that is. So now when we were going through the process of deciding what to do here, when we decided to build asterisk SCF and then went and did a bunch of research on what we would build it on top of, obviously we looked at lots of things. There's, you know, distributed applications, object-oriented middleware, whatever word you want to use. They've been around for a long time, probably since, I don't know, maybe even in the 70s there may have been some things around. And there's lots and lots of stuff out there. We did not choose anything that most people had ever heard of before, because every time we looked at it, it wasn't flexible enough. It either restricted what application languages or what programming languages you could use to build things. It restricted deployment models, or just all kinds of other things. ICE was actually the only platform that really fit our list of requirements. And I guess a tiny funny story there. A gentleman who used to be with Digium, Brian Degenhardt, who was one of the founders of SwitchFox, he and I were the ones that were tasked with going off and figuring out what asterisk SCF was going to be, what tools it was going to be built on top of, and all that kind of stuff. And we'd spent, I don't know, probably the better part of 4 months looking at various messaging platforms, building prototypes to see how fast they could transfer messages and all this stuff. We'd never come across ICE at all. And as we were getting closer into building the project, Ken Hunt, who was a friend of our VP of Engineering, had heard about what we were doing, was interested in it, and sent David an email and said, hey, have you guys looked at this thing called ICE from Zero C? And David sent it to me, and I said, no, I've never heard of this before. We spent 4 months looking at stuff. We never found this before. In 5 minutes, I'd gone to their website and realized this was the thing we'd been looking for 4 months. It was really incredible. And somehow we never found out about it. So we've let them know they need to do better marketing, because obviously we never knew about their product. So the choice then was clear that this was the right tool to use to build our stuff on top of. ICE was not built by people who didn't have experience doing all of this stuff. Everybody who's working on, or who designed and built ICE, and pretty much everybody's still working on it, are people who've been in the object-oriented middleware business for a long time. Many of them worked at major Corba companies and all these other things for years. And there's some similarities in what they've done to what Asterisk did in the telecommunications world. Corba is, I was going to say works, I think I'll say is usable instead, because it is usable. It's just very, very hard. It's very big and complex, and there's 17 different ways to do the same thing, and you can go buy 3 products from 3 companies that all claim to be Corba compliant, but they won't talk to each other. It's really, really just mind-bogglingly bizarre. Well, the telecommunications world is exactly the same way, right? At least prior to open source and the advent of inexpensive telephony was exactly the same way. You couldn't go buy 2 different major brand PBXs and expect to just hook them together and everything would just work. It didn't. So they went through some of the same things. They said, look, this idea of an object-oriented platform that you can use to just distribute applications, people need this. Developers need this. They need to build these kind of applications. But the things that exist out there are too big and too complicated. They're designed by committees. Everybody knows how design by committee results in usually not the best product and lots of other things. So these, I think, 4 people went off and just said, we're going to make our own. And they made their own, and also decided to make it open source, just like Asterisk is, and that's how we ended up where we are. Come on, move. There we go. So, like I said, it's really oriented around developers. In fact, one of the very first really astonishing things that I saw about this platform, which hopefully we'll be able to achieve even half of this with asterisk SCF, is I went and downloaded ICE to start playing around with it, looked on their website for documentation. The documentation is a 2,000-page PDF. And my first thought was, oh my God, an open source project with 2,000 pages of documentation. This is incredible. I've never seen anything like this before. Well, That's a little bit misleading in that it's full of examples, and the examples are presented in 6 different programming languages, which is really awesome if you're familiar with one of those and not all the rest. Their examples do identical things. They're just written in 6 different or 5 different languages. So that consumes part of it. But in the rest of it's extremely well documented and very well tested and it's very easy to understand. And all of the examples that are in the documentation all come with the source code. You can go test them all yourself, and it's really very easy. And it's really designed for someone who's familiar. Let's pick an example language, Java. There may not be anybody in this room that likes Java. There might be lots of people in this room that actually detest Java. I don't care. It's as good an example as anything else. The idea here is that a Java developer wanting to write a component that uses ICE, and in our case is an asterisk SCF component, should be able to use the mechanisms and things they're already used to using in Java without having to learn anything really new. So if there's an object that's been presented to them that has an operation on it called, I don't know, start, and it takes 3 parameters of different objects, they should just be able to call that, just like it was any other Java object. It shouldn't matter that that object actually exists on a machine that's 1,000 miles away, and the system is connecting to it over an IP network. So that's really the way ICE was designed, and it makes it very, very straightforward for people to get started with things. Yeah, there's lots of really very technical details there, but another thing about this is ICE is not compatible with anything else and doesn't want to be compatible with anything else. It doesn't use XML, it doesn't use JSON, it doesn't use anything else. It uses its own protocol to talk between all of its endpoints, which is binary, very efficient, and supported across all those different platforms and things that we talked about before. So because they're not trying to be compatible with any other platforms, that means they're not constrained by what those common protocols say that you have to do. Let's see, how am I doing? Oh, good. I think we've already covered most of this stuff, so we'll skip that slide. Again, very similar licensing, in fact, almost identical licensing to asterisk. It's available to everybody under GPL version 2. It's also available under commercial licensing with support behind it and bug fixing and all that kind of stuff, just like asterisk and eventually asterisk SCF will be. And they do I would say that, and I don't mean this in any kind of detrimental way, ICE is an open source project in the same way that lots of other things are open source projects, like, let's say, MySQL. MySQL is also an open source project. You have all the source code available. You can patch it as much as you like. But if you watch the development of MySQL, the work that goes into it is almost exclusively coming from people that, who is it now, Oracle, I guess, that owns MySQL, that they pay to work on it. It's not the kind of thing that most people are just going to go write a small patch or even a complex patch and contribute. Now, I would have originally, if someone had originally told me what asterisk did, I would have thought it was the same thing, that most people were not going to go write patches for telephony platforms. Yet, there's lots of people in this room that do and have provided patches to us for asterisk. ICE is kind of in that first camp. There are parts of ICE that have come from outside of Zero C's development team, but almost all of what is in ICE and what continues to happen in ICE comes from their development team. But their development team is readily accessible. I don't think they're on any real-time networks. We don't have them on IRC or anything, but they provide forums and email support and all kinds of other stuff. They're very, very easy to work with. So, and we'll do a little bit of marketing here, I guess, for them. ICE has been used in some very, very large deployments. I probably have to tell them to take that HP one off because that network's being shut down now. So that's probably not a good example anymore. It's no reason, not ICE is their problem. It's just HP can't ever decide what they want to do. So, but really, it's the kind of applications that get built on top of this are the kind of applications you're never going to hear about. They're the things that, you know, a Fortune 100 company with 15,000 sites around the world built to manage some part of its system to operate their company. You don't know that they built that. You just know that maybe their prices got better or they're offering new products they didn't used to have or whatever it is. So you don't really hear about this kind of stuff. Even the usage of ICE in Skype, it's not used in the Skype client, for example. It's used in the back-end network that they do for call routing and a bunch of other stuff. at least as far as we know. We know it's not in the Skype client. And there's some interesting things it's been used for as well. Here's an example of something that was just done in the last year where it's being used to communicate between these robots that are talking to each other. There are some other open source projects that also use ICE, although none of them are really huge, household names, things you would have heard of or worked with before, I suppose. So we're expecting, if asterisk SCF ends up going anywhere like what asterisk did, we'll probably end up being the largest, most prominent open source project that's using ICE for a while. And then there are binaries of it available, although Josh is going to talk about later. We have made a bunch of our own changes to ICE, which we're in the process of getting pushed upstream to 0C. And so for now, at least, you have to use our version of it. So what does this all mean to you? How is this useful? Well, what it means, like I said, is you get to write extensions, components, whatever you want for asterisk SCF in pretty much your favorite programming language, as long as it's a real object-oriented language and not something that can't handle that very well, which means it's very, very flexible. In fact, in February of this year, the first time we demonstrated any of this, I went to Brussels to speak at an open source developer conference there and showed people I can't remember, I think it was 4 different versions of a 20-line or so hook for asterisk SCF. You'll learn what that is in a little while. That handles SIP authentication. Requests come in over SIP. We need to decide whether we're going to request authentication or not and what the username and password is going to be. In an asterisk SCF, that's not something that's hard-coded in the system. It's provided by some component that says, yes, I want to authenticate this call. Or it might even be a call, I suppose. I showed, I think they're 20 or 25-line examples of the exact same thing written in C++, C#, Java, and Python. They all worked exactly the same way. And in fact, you could actually read anybody who's a even moderately competent programmer would be able to read it and see what it's doing, even though underneath what it's doing is incredibly complicated. There's all of this machinery to connect between systems and all this other stuff. You don't have to deal with any of that. Another benefit of this, from a developer point of view, is what's, I guess it's the third real bullet point on here, is that what you write isn't a modification of the asterisk SCF code itself. It's not like working on asterisk, where let's say you're going to go write a patch for ChanSIP, which Klaus does fairly often, and you want to go test it. Well, if you've done something wrong, and maybe you have a memory leak, or worse, you have access to a pointer that's been freed or something like that, it's very likely what's going to happen is you're going to crash asterisk, and you're going to have to go figure out what went wrong and all that kind of stuff. Using a distributed platform like this means you can have a whole set of systems that are running the standard asterisk SCF components. You've got them all configured, they're running, they do what they want to do, and then you're playing around with, I don't know, a new way to authenticate incoming calls. So you've written a new component to do that. When you start it up, it connects across the network to that existing cluster, registers itself as a service that's going to be used, and then it gets used. If it crashes, well, it just goes away. It's not like the rest of the system is actually affected at all. I mean, what you were using it for obviously stopped, but it didn't crash any of the rest of the system. And if the rest of that system was doing real work, it's still doing that real work. You haven't destroyed it by trying to run some test code in it. So, okay. How much do I want to do here? We'll go through the rest of these slides really fast because there's not a lot. We don't need to spend a whole lot of time doing this stuff. This presentation is actually on the 0C website. If you want to go through it in much more detail, you're welcome to do so. In addition, that 2,000-page PDF is there, and their training materials, the basic training materials for learning how to use ICE are all there, are also available for free. And you probably can't read most of that text because it's pretty small. But this is really the gist of what's happening, right? Someone, somewhere, for some reason, has created this object. It's called XYZ. It lives somewhere. You don't even have to care where it is. It could be on the same machine. It could be somewhere else. In a piece of software that you've written, someone has given you the details of how to connect to this object and use it. Ask it to do things for you or to receive data back from it. And so, in this case, it just happens to be a string of text that just says, it's on this machine called it's actually called XYZ. I want you to connect using TCP to a host named host, and it's listening on port 10,000. That's all you have to know. And once you've given that information to ICE, it will actually go verify that that object exists, that it's the type you expect it to be. It's not some other kind of object with a totally different interface that you're not used to working with. And then say, yes, you can now use this object as if it was written and running inside your client application. I'm going to skip this because you guys are talking about slice later anyway, right? Yes, no? A bit? Okay. Well, okay. So we'll go through this really quick. So there's been a couple mentions so far of the fact that ICE is I can't remember. There's no better way to say it, so I'm just going to say what it is. It's strongly typed middleware. For those of you who've done object-oriented programming, hopefully you'll understand what that means. It means that, unlike, for example, how many of you have done development of JavaScript to any extent at all? Okay, enough. So you understand what JSON is, right? JSON is, for lack of a better way to say it, it's a bag of stuff. You can throw anything you want in it. It can be structured any way you want. And when you send it to some other piece of code that wants to interpret it, it has to be structured in the right way, or that code is not going to work correctly because, well, you haven't named the objects inside it correctly. Or instead of making something an array, you've made it a hash, or whatever it is. It just, your code ends up breaking. That is the nature of things like JavaScript and other languages that are not strongly typed. They let you do anything you want. Well, of course, again, with great power comes responsibility. ICE does not work that way. In ICE, if we have something somewhere out in the world that implements this interface called printer, it has an operation on it called print string, which you pass a string to. That's it. That's all this particular little interface is. You don't have to know what language the thing that's implementing that was written in, or what machine it was running on, or whether it uses big endian words or little endian words or anything. None of that is even relevant at all. You have a contract between, in this language called slice, that this is what it's going to do. If you invoke this operation, you'll be able to pass this kind of parameter. In this case, you don't get a result back, but that could be specified there as well. This then, there's no example of this here. This, using tools that come with ICE, that file, which they're called printer.ice, actually gets translated into the language you want to build in. So if you want to build in C++, you run a tool called slice to CPP. It generates a C++ header file and a source file with all the things that you need, so that in C++ you have the ability to have a pointer to a thing that implements the printer interface. And as far as you're concerned in your code, you just have a pointer to an object, and it has an operation on it called print string, and that's it. You have a question, Alex? Mm-hmm. It depends. So his question was about, I'll rephrase your question, you can tell me if I'm wrong. His question was, how generic is this translation? It's not at all. There are separate translators for every language that's supported. So the C++ one, since there's no such notion really as reflection, generates complete C++ header files and source files with classes you derive from and all the sort of things that a C++ programmer would be used to doing. The C# one and the Java one are very similar, but of course those languages have some slightly different mechanisms for doing the same sorts of things, so those are used. But when you get to things like Python, there's actually two ways of doing it. There's the same way, this static generation thing that generates a bunch of Python, which gets emitted into a .py file, and you can just load like any other Python module. There's also totally dynamic generation, where you can just load up a Python interpreter and say, hey, I want to go use that slice file right there. And it just generates a bunch of stuff in your Python process, and you have all the class definitions and everything else there for you to use. So. Yes, yes. So the slice language itself, its own language specification, it does not have anything in it that could not be translated into all of those languages. So there's a bunch of restrictions. For example, there's restrictions in it that we don't like because maybe Java can't do that. So you would look at this and go, oh gosh, it would be, I can't remember what the one, for a while they didn't let you have, oh, what's the really nasty one? The naming thing. You can't have, if you define a class, let's say, well, this is an interface. That's good enough. This is an interface called printer. They've got an operation there called print string. Just for this hypothetical example, let's say you wanted to name the parameter to that printer. You can't, because there's at least one language that slice can be translated to that doesn't allow any entity inside of a class definition to have the same name as the class. And all of us that are C++ programmers or Java programmers or C# programmers go, well, this is just dumb. I can do this all day long in C++. But you have to be the lowest common denominator here, so there's some things you have to work with there. So really graphically, I guess, this is really what it ends up looking like. There's all these blocks and bits and pieces. Some of these things are things that you wrote. Some of them are provided with ICE. For example, the two big blocks there are provided by ICE. This object adapter is also provided by ICE. And then these little pieces right there, well, I guess they have them marked there, that's hashed. These little gray bits are the things that the translator produced, and then the stuff at the top is what you wrote. So all of that mechanism is all just taken care of for you. You don't have to, I mean, you can dive down in there and mess with it and do whatever you want to do, but it's all, at least at the basic level, it's all handled for you.
This may have been on one of the slides, but I can't see your slides at all.
Okay.
But is this just IPv4 or is it IPv6? What are you limited to transferring it over?
Okay, the simple answer is you're not limited at all. The more direct answer is it already supports IPv4 and IPv6. It supports transport over TCP or UDP. You can choose based on what your application is suited for. Obviously, if you use UDP, you have to worry about things like it might not get delivered, or packets might get delivered out of order and things like that. It also supports SSL and TLS encryption on top of TCP. And this ICE core, the transport mechanism, is actually a plugin, which means you can write a plugin to transport over anything you wanted. So if you have an application that would benefit from using SCTP, for example, or if you're really old school and you want to use IPX on a NetWare network, you could write a transport for that and it would work, and all the stuff at this level and above would really not have to care, because all it needs to know is there a way that I can specify where that object lives by typing in some string, some address that will resolve to where that thing is. That's all it has to have. What's that?
All it needs to know is can the data get there?
Somehow it has to have a way for the data to get there. Yes, that's it. So, oh, Alex, yes. No, it does not. Nope. No abstraction layer on top of UDP. In fact, you're only allowed to use UDP with a particular type of proxy inside ICE that's a datagram proxy, so that you understand that you're on your own for stuff getting there in the right order, or getting there at all, really, for that matter. So, but then you could just use TCP. So you could do that. That's right. There's a lot of different ways you could approach that. Yes. So, okay. So we'll just do a really brief example of what slice is. We've talked about it enough. You've probably already gotten a little bit of an idea. It's a language. It's what's called an interface definition language. That's actually a generic term, even though Corba's interface definition language is actually called IDL, but they don't get to monopolize the acronym. So. It's what you're going to expect. It's got types for data that you can transport around, numbers and strings and enumerations and structures and sequences, which would be arrays, dictionaries, which would be maps for those of you who've used those kinds of things before. Classes, exceptions can be thrown back and forth across ICE connections and all of that kind of stuff. And you use this to tell the system what kind of objects you're going to have, what interfaces they expose, what kind of data they're going to transmit and receive amongst each other. And then those translators write code to actually make all of that happen for you, so you don't have to do it. I think I'm going to skip this really detailed stuff, or at least go through it really quickly. The basic, most common thing, which is why this is the first slide, this is some object lives on some server somewhere, some client wants to issue a request, the request goes over, it waits for the response to come back. When the response comes back, the client continues processing. That's the most obvious, simple things, of course. There are other ways to do it as well. It's called asynchronous invocation. You can send the request off to the object and then just say, hey, when the response comes back, call me back over here and let me know what happened. If I get an error, did it work, did I get an exception, whatever. And you can go off and do whatever you want to do. And eventually, hopefully, the response will come back from the server and the ICE runtime will call your callback and say, hey, here's your answer. What would you like to do with it? Yes, sir. So the question was, is it possible to make the callback null? Well, yes and no. Because of the way the language is defined, it's always possible to receive an exception. So for example, you could try to invoke that request and the object isn't there anymore, or the server's dead, or you've lost connectivity to that machine. And you would want to know that. Most likely, you would want to know that. However, there are applications where that's useful. And in ICE, there's a type of proxy, that mechanism that's used called a one-way, that's one-ways, where that's literally what it is. It's fire and forget. You're not even going to know if the server wasn't contactable. So there are times you may want to do that, and that's available. So.
Like telling some module or server to reboot, not to reboot it, it's not going to be able to send a response back to you.
That's certainly possible, yes. So the same sorts of things are true on the server side. If you imagine now you're writing the server side of this link instead of the client side. If a client sends you a request, your callback's going to get invoked and say, hey, somebody called your print string operation. Here's your parameter. Go do whatever you're going to do. In the most simple cases, of course, you're going to go do that work and then issue a response that goes back to the client, and that's that. Now, the interesting thing here is that you don't have to know, actually you won't know at all, whether the client issued that request to you asynchronously or not. That's not relevant for you. All you need to know is about what you are doing. There is then also an asynchronous thing on the server side as well. So you can receive the request and say, well, I'm not really ready to do this right now. Let me package up all the details about this request, and I'll store those maybe in some kind of task list that I'll get around to when I'm ready to get around to it. And then when I'm finished with the work, ICE has provided me a callback. I can say, I've finished this, and here's the result, or here's an exception, or whatever it might be. That's all you're... Alex, go ahead. The most obvious ones are things like object not found. So we were able to talk to the server that you told me the object was on, but it says that object doesn't exist. Then there's also things like the connection itself could not be established. I don't know how far you can dive down into finding out why, if it's even possible to find out why. Because I don't know we've even tried to do that yet. But the data's there. I mean, it's that's another interesting thing. We're getting off into a little bit here, but all of the interfaces into ICE itself that are provided for you are themselves defined in Slice, which means you can go dive down into all of this stuff. If you've received back an object, from ICE, an ICE runtime exception, you can actually go query it for all kinds of information and get other stuff back. It's pretty interesting. So this did not render properly, so I'm not sure this is really going to be very useful. And it's probably too much detail for this at this point, plus I'm at 45 minutes. So we'll cover just some other basic stuff. The ICE platform, we've talked about it being able to be used to connect clients and servers together, lots of different ways, whatever languages you want. The ICE toolkit actually has a lot more stuff than that as well. So some of these tools we don't use in asterisk SCF, although they exist, but I'll just briefly cover them so that you know that they're there. You can imagine before I said, okay, you have to have this string that identifies where an object is so you can go talk to it. Well, what if you don't want to have to distribute that information all around via configuration? You'd like to be able to discover it. There's a tool that comes with ICE called icegrid, that's exactly what it's for. You can send requests to it and say, I need something that matches these parameters, sort of. And it will give you back proxies to one or more of them that exist, that have been registered in the registry, which you can then go contact. And that tool itself has its own replication mechanism, so you can have multiple replicas of that same registry, and it doesn't matter if one of them goes down, you just talk to the second one and it has all the same information in it. So that's a pretty nifty thing. There's another aspect of icegrid, which again we don't use in the asterisk SCF world. It actually comes with a graphical administration tool that can be used to actually push components out to machines and start and stop them and reconfigure them and lots of other stuff like that. This is a tool that's called icestorm, which we do use. This is used for, well, like it says, publish and subscribe mechanics. So you've got a situation where you've got something that produces data, you've got something else that wants to consume that data, but they're never actually aware of each other's existence. They just, if you think about like a logging system, for example, where you're just going to spit out log messages, something out there is going to care about them, but you don't know who they are, and they don't even know where the log messages are coming from. You need this mechanism to connect them together. This is what that's for. So icestorm allows you to create things called topics. You just create a topic, give it a name. The topic can only carry data of a particular type. You have to tell it what type of data that topic carries. And then when publishers publish data into it, it's distributed out to anybody who's subscribed to the topic to receive it. It supports federation. You could have lots of levels of ice storms with them all linking together, and it of course supports replication and lots of other things as well. So we use this for event distribution. I think the logging system can use it right now, and there's some other bits and pieces and for configuration data. So this is a really powerful tool as well. And of course, again, since it's all open source, we have the source code for that too. If you want to go change the way it works, you can do that. Now, you've probably gotten the hint at this point. ICE does not use HTTP. It doesn't use SSH. It doesn't use any other protocol you've ever heard of before. It speaks the ICE protocol between two endpoints, which means that if you need to traverse across a network boundary where you can't just open a TCP connection directly to port X on server Y, something's going to have to help you do that. The most obvious examples, of course, would be you're running something you've written in ICE on a handheld device on a GSM network or something on a Wi-Fi network or whatever it is, and you want to be able to get inside the network and talk to stuff that's in there. There is a tool that comes with the ICE toolkit called Glacier 2. You may have noticed a theme to the names of all of the tools there. That's exactly what it's for. So it sits right at the edge of your network, well, actually right behind your firewall. It does actually use, it's not HTTP, but it uses SSL over TCP connections between the clients and Glacier, and then it distributes stuff inside the network. And it has lots of useful mechanisms for authenticating users, even using SSL certificates if you want to do that, and controlling what they have access to on the inside of the network, and lots of other stuff. We will eventually be documenting how that would be used with asterisk SCF and showing people simple clients that they can try on the outside of the firewall and stuff like that. We just haven't gotten that far yet. I don't think you can tie two glaciers. I mean, well, I guess it depends on what do you mean by tie them together. You mean for redundancy or two steps?
Like, okay, say I've got a bunch of stuff over at a data center that, say I've actually got my asterisk SCF cloud over at the data center, but I've got the bunch of the application and data source is at our office.
Mm-hmm.
And I want to, that's talking ICE also, I want to tie them together, the ICE connection together.
You'd probably just use some kind of traditional tunnel for that. VPN, IPsec, whatever you wanted to use there. It would be simpler than this because this is a proxy. It's like actually it's more like a router, to be honest. And so it changes the way things are configured and operated in ways you wouldn't want in that kind of situation. So There's another tool that comes with the ICE toolkit, again, that we don't use, but you can imagine, again, it's got a nice relative name, freeze, which is used for if you've built a server, you've got a lot of objects living in it, and you want to be able to persist them in case the server gets shut down, either intentionally or unintentionally. It can actually push them all out to a database, and then when the application comes back up, be able to recover all of those objects right back from the database. And I think we'll skip that one because we don't care about that. Now, one of the things I didn't stress before, I guess I did talk about this stuff, Windows-related stuff before. All of this stuff that comes with the ICE toolkit runs just fine on Windows as native Windows services. And in fact, all of the components that we built for asterisk SCF also run just fine on Windows as native Windows services, if that's what you would like to do. So about half of our development team does their primary development on Linux, the other half does it on Windows, and then we all do our testing on both platforms and all that kind of stuff. So there are lots, for people who are just more comfortable, for example, deploying services on Windows, that's fine. They can absolutely do that. So, and I think that's about that for that presentation, which means I'm done. So let me get this ready for next one, but I can take your question.